Welcome to Lecture 32. This is on Green's theorem, the flux form in 2D. And so we're going to basically illustrate Green's theorem on a connected, not simply connected region. So this is more or less following up from the previous lecture. The material being covered here is from Reading Assignment 4, Section 4.1.3. And more or less the concepts visualization skills are to introduce a cut in an annulus and compute the flux from an annulus. As usual, the second slide just an outline of what is to follow, so we'll just skip over this and move on to the next slide. So the problem statement is to compute the flux exiting the boundary of an annulus using Green's flux theorem and show that the right-hand side and left-hand side give the same results. We're going to assume a vector field F in region R given by the expressions that are shown, one for F and one for R. They're basically here. And so we start basically by drawing a picture of the region as described, which basically involves a region between a circle of radius 4 and a circle of radius 1. So this is 1 and this is 4. And so this is effectively the problem that we're looking at. So this problem, as shown here, is basically not a problem that we're able to solve using Green's flux theorem. And so the simplest solution is to introduce a cut to make the region simply connected. And so this cut is shown here, circled in red, right? And so from the previous lecture, we showed that we could essentially draw a contour consisting of 4 segments that basically enclose the region, in which case, in this case, we are able to use Green's flux theorem. All right, so we're going to compute the flux using the left-hand side and right-hand side of Green's theorem. I've basically shown the picture for the vector field and all the salient things of interest to us in computing the flux. So for example, N1, which has to be pointing outwards, we're going around the closed contour in a counterclockwise direction. Again, always looking to your right. So N1 is pointing outwards on this outer circle. Moving in this direction, it'd be pointing in this direction to your right. Going in this direction, it's pointing to your right, which is in this direction. And finally, along the last part of the segment, the fourth segment is pointing to your right, which is this one. So you got 4 individual segments, and the direction vectors normal to the contours are basically provided. And this in red is the vector field. If you want to look at it, you can. It's accessible at the URL that's sort of shown here. All right, so we're going to apply Green's flux theorem using the figure to the left. And so on the left side, it's a closed contour integral of f dot ns ds. Right? And this is equivalent to the divergence of the vector field integrated over the area enclosed. And that's equivalent to df dx plus dgy dA, where f is this term here and g is this term here. All right, since this contour basically consists of 4 segments, we've written it out as follows, like this. And also, we make note of the fact that when you go in this direction and then in this direction, you get cancellation taking place because the normals are in opposite directions but the same. So that means, for instance, the fact that this f dot ns3 ds equals minus f dot n4 ds, when we add this term and this term, essentially these two cancel. And so we're just left with this integral and this integral. And so that's basically the objective then, is to compute this integral and this integral. Alternative, if you wanted to, you could reverse the direction of C2. So instead of basically going in this direction, you could go in this direction for this particular interval. And that would mean this becomes a minus C2. But if you change the direction on the contour, then this sign has to change with it as well. So this would become minus f dot n2 ds. Even though you're keeping n2 in this direction, you'd have to invert the sign. So you put a minus here. So this is effectively the calculation that we're going to be performing. All right, so now let's do the actual calculations. That is, compute the flux. starting with the left-hand side of Green's theorem. So if we look at our picture here, we have one contour C1, which is around the circle here in a counterclockwise direction. Then we come across, which is contour C3. Then we go in a clockwise direction, which is contour C2. And then finally, we come out contour C4. And we mentioned earlier that the only contributions to the contours would be this one here, C2 and C1, because these two contours in the opposite direction will be canceling each other out. So what we need first of all is the position vector for C1, a position vector for C2, from which we can then do the necessary calculations. So for position vector for C1, the radius of this circle is 2, so simplest parameterization will be 2 cos theta, 2 sine theta, where theta varies from 0 to 2 pi. So as theta advances, the position vector will basically move in a counterclockwise direction, which is what we want, and so this is the correct parameterization. Now, to determine the normal component, again, the normal will always point to your right if you're basically moving in a counterclockwise direction. And so from previous formulas, we would compute x theta and y theta, and then we would reverse the roles and then multiply the right hand by the negative sign. And so we can basically take the derivatives of x dot and y dot, place the resultant values in this form, and this gives us the vector that represents the normal to the contour. So this would be 2 cos theta, 2 sine theta d theta. For a position vector C2, which is in a clockwise direction, we would find a parameterization of the following form, from 0 to 2 pi, and of course this is a radius of 1 for the inner circle. Similarly, we could determine the normal, which would be basically always to your right, and so this would be pointing inwards in this case. And so if you do the necessary computations, you'll end up with the normal component having this form. And the field was given as xy squared x squared y. All right, so now we can compute the integral because we have both the information regarding the normal component, and we also have the field value, and the values of x and y squared that are substituted here are based on the parameterization. So for instance, if we look at contour C1, which would represent this integral here, here is n1 ds, and this would be xy squared x squared y, where x basically is going to be, you substitute 2 cos theta, and for y you substitute 2 theta, and you can see now that the vector is only a function of theta. And so you take the dot product and integrate with respect to theta. The second term, which represents a contour integration of closed contour C2, in this case, basically, we'd be using the second position vector, x is cos theta, y equals minus sine theta, substitute into here to obtain this expression that you see here. And this represents the normal component to the contour on the innermost circle, which is this term that you see here. Take dot product and integrate between 0 and 2 pi. Anyways, the rest is mechanics, and you'll find that you'll get an answer of 15 pi over 2. All right, so now let's basically redo the calculation on the right-hand side of Green's theorem. Again, this is the field vector that we're dealing with. So we need to take the partial of this f with respect to x and add it to the partial of g with respect to y. If you do that, you'll end up with x squared plus y squared dA. So the next thing basically is to do this double integral, and given that it's circular, it would be appropriate to solve this integral in polar coordinates. And so in polar coordinates, the transformation is x equals r cos theta, y equals r sine theta. And the region basically is bounded by a circle of radius 1 and a circle of radius 2, and theta spans from 0 to 2 pi. So this is the boundary on the integrals, 1 for r, 1 for theta. This is the transformation. And of course, from this, you can compute the Jacobian, and so dy dx maps over to r dr d theta. So this expression in polar coordinates just becomes r squared, r dr d theta. First integration is with respect to dr, between 1 and 2, and theta is between 0 and 2 pi. If you follow through and do this calculation, you get 15 pi over 2, which basically says that the right-hand side is in agreement with the left-hand side. So clearly we have shown here with the technique that was basically developed in the previous lecture, that in fact, in this case where you start with a not simply connected region, that by introducing the cut, we can still employ Green's flux theorem and basically see agreement between the left-hand side and the right-hand side. So that concludes lecture 32. Thank you for listening.